Hello friends, welcome to the session, that is chapter 2 itself, that is power semiconductor devices, thyristor concepts I am discussing. In the last session that I explained what is the necessity of series connection. In that mainly I define what is string efficiency and what is the derating factor. Okay. And what is the significance of string efficiency, what is the significance of derating factor, that I discussed. Now the another concept I started, that is I want to discuss in detail about series and parallel connection. In the in detail discussion of series connection, that you will see continuation, that I told that even though SCRs with same rating and same specifications, practically SCRs are not blocking the same voltage because of unequal voltage distribution. That is because of unequal static VI characteristics, there exists a unequal voltage distribution. Due to unequal voltage distribution, the string efficiency is reducing. This is one problem in series connection. Okay, here I am discussing in detail about series connection, that we concentrate. This is a continuation of previous concept. I am discussing in detail about series connection. I told that always string efficiency is practically string efficiency is less than 1. Ideally string efficiency equal to 1. Why? There is a unequal voltage distribution due to unequal static VI characteristics. Yes, this characteristics that I drawn already. Yes, this you know. Because of unequal static VI characteristics, this anode to cathode current, this anode to cathode voltage. Yes. Then this is the static VI characteristics of one SCR. Okay. And this is the static VI characteristics of another SCR. Yes. Due to unequal static VI characteristics, we are getting unequal voltage distribution. This is forward breakdown voltage. If you draw the characteristics for, if you consider for same leakage current, this is V2 that I given, this is V1 that you see. This is the static VI characteristics of T1 thyristor, and this is the static VI characteristics of T2 thyristor. This characteristics I given, this is the static VI characteristics of T2 thyristor. Okay. For same leakage current, where IB I given that leakage current, T1 blocking the voltage of V1, T2 is blocking the voltage of V2. Then I define what is the string efficiency. String efficiency equal to voltage across whole string by number of series connected SCRs into individual voltage rating of each SCR. In that I take an maximum voltage consideration. Okay. Now because of this, what is the problem? String efficiency is less than 1, that is string efficiency is reducing. This is the problem. That means I am discussing in two cases. In series connection, the case 1 is case 1. Under case 1, cause is unequal voltage distribution due to unequal static VI characteristics. Unequal voltage distribution, unequal voltage distribution that is due to unequal static VI characteristics. Unequal static VI characteristics. Unequal voltage distribution due to unequal static VI characteristics. This is the cause in series connect. This is a problem. Okay. Unequal voltage distribution due to unequal static VI characteristics. Then what is the remedy for this problem? What is the solution for this problem? That I want to discuss. What is the remedy? Remedy in the sense, what is the solution for this problem? Yes, listen please. We know that if the thyristor is under forward blocking mode, there is a unequal voltage distribution, there is a leakage current is exist. Remedy in the sense, you want to improve the string efficiency. Unequal voltage distribution due to unequal static VI characteristics. Due to this, what happening? Due to this, string efficiency is reducing. Now remedy in the sense, to improve the string efficiency. You want to improve the string efficiency. If you want to improve the string efficiency means you want to equalize the voltage distribution. Clear? What is the reason for string efficiency is reducing? Because of unequal voltage distribution due to unequal static VI character. The remedy in the sense, to improve the string efficiency, to improve the string efficiency, it is required to equalize the voltage distribution. 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 Yes, understood. This is the cause. Due to that, string efficiency is reducing. To improve the string efficiency, it is required to equalize the voltage distribution. Then how to equalize the voltage distribution? Yes, listen please. If the SCR is under forward blocking mode, this is T1 SCR, this is T2 SCR. Let T1 is blocking the voltage of V1, T2 is blocking the voltage of V2. Now, under forward blocking mode, which current is exist in the SCR? Is there any forward current? No, there exists a leakage current. That current is called forward leakage current. Then let assume that both the SCRs are carrying the current of leakage current of IB. Means under forward blocking mode, there exists a voltage and current also. Na? Then we can define leakage resistance of each SCR. Now see, what is the leakage resistance of T1? Leakage resistance of T1 is V1 by IB. This is a leakage resistance of T1. This we can write as a RL1 is equal to V1 by IB. Then what is the leakage resistance of T2? Leakage resistance of T2. Leakage resistance of T2. That I denoted as RL2. That is V2 by IB. Okay. I am finding remedy. For that, first I am defining the leakage resistances. Understood? That means if the SCRs are under series connection, each SCR offers different leakage resistance. Each SCR offering different leakage resistances. For example, let us assume that n number of SCRs are connected in series. N number of SCRs are connected in series and so on. Okay. N number of SCRs are connected in series. Then Each SCR offers this equivalent I am representing as a leakage resistance. The SCR equivalent I am representing as a leakage resistance. Then each SCR offers a leakage resistance of RL1, RL2 and so on RLN. Because of unequal voltage distribution, each SCR blocks different voltages. Due to this unequal voltage distribution only, string efficiency is reducing. Now tell, just think. Means indirectly the unequal voltage distribution is due to unequal leakage resistances now. Understood? That means you want to equalize the voltage distribution means it is required to equalize leakage resistance. It is required to equalize the leakage resistance. Understood? If you want to equalize the voltage distribution means it is required to equalize the voltage. It is required to equalize the leakage resistance. That means to equalize the voltage distribution, 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 it is required to equalize. It is required to equalize. It is required to equalize. Which one? Leakage resistance. Leakage resistance. Yes, tell me. It is required to equalize leakage resistance. Now, how to equalize the leakage resistance? Different SCRs are having different leakage resistances. If you want to equalize the leakage resistances means we can connect the resistances, different values of resistances in such a way that the leakage resistance of all the SCRs must be equal. That means we can connect different values of resistances. This is R1, this is R2 and so on. This is like that Rn. Like that we can connect different values of resistances in such a way that we can bring all the resistances are equal. In such a way that all the resistances are equal. If all the resistances are equal, then each SCR blocks the same voltage. Each SCR blocks the same voltage. But practically, is it possible? One string means number of SCRs are connected. Then we can design the resistance, different values of resistance in order to make all the SCRs are having the same resistance. But practically it is a complex process. Understood? That means one method of equalizing resistance is to equalize the leakage resistances across each SCR. Different values of resistances are connected, but practically it is a complex process. Understood? That means to equalize the leakage resistance, to equalize the leakage resistances across each SCR, different values of resistances are connected. Different values of resistances are connected. Resistances are connected. Yes, different values of resistances are connected. But practically it is a complex process. But it is practically complex process. Selecting the different values of resistance, designing the different values of resistance is a practically complex process. Then what you can do now? One method is to equalize the voltage distribution. We want to equalize the leakage resistance. To equalize the leakage resistances across each SCR, different values of resistance we want to connect. But I am telling that it is a practically complex process. Then for approximate equalization, not exact equalization. No need to bring exactly 100% string efficiency. Not possible, na? Then, for example, string efficiency is 30%. We want to improve up to 50%. We want up to 60%. Or we want up to improve 70%. Like that we want to do. Then, that's why, for approximate equalization, not exact equalization. For approximate equalization, one value of resistance is designed. That resistance is connected across each SCR. For approximate equalization, one value of resistance is designed. That resistance is connected across each SCR. Then that resistance is called static equalizing resistance. Then that circuit is called static equalizing circuit. Understood? Why I am telling that it is a static equalizing resistance? Yes, it is equalizing the static characteristics. We are equalizing the voltage distribution, means indirectly we are equalizing the static VI characteristics. That's why this resistance is called static equalizing resistance. Then the circuit is called static equalizing. Now I want to represent what exactly static equalizing circuit. From that static equalizing circuit, now I want to design the resistance for approximate equalization. This is a design value. How to design that static equalizing resistance, that you can see. Then that statement I am writing, concentrate. Clear? Understood? Then what I am doing here? I am not doing exact equalization. That I am doing for approximate equalization. I am doing the approximate equalization. Yes. Then for approximate equalization, not exact, for approximate equalization, one equal resistance is connected, one equal resistance is designed, and it is connected across each SCR. This resistance is called static equalizing resistance. Static equalizing resistance. And the circuit is called, static equalizing circuit. Okay, static equalizing circuit. Okay, now we'll see what exactly static equalizing circuit and design of static equalizing resistance. That you concentrate. Okay, calculation of static equalizing resistance. resistance. This calculation of static equalizing resistance. Yes, let us consider n number of SCRs are connected in series. Let n number of SCRs are connected in series. N number of SCRs are connected in series. N number of SCRs are connected in series. Okay. Then let the total string voltage is Vs. Vs is the string voltage. Total string voltage is Vs. Okay. Then for approximate equalization across each SCR, one equal value of resistance we are connecting. Across each SCR, one equal value of resistance is connecting. Yes, let this is R and this is also R and this R we want to design. This circuit is called static equalizing circuit and the resistance is called static equalizing resistance. Let this total I am dividing into, because I want to derive one generalized formula na, I am assuming that this one SCR belongs to one category, means it blocks one voltage. I am taking like this, one SCR belongs to one category. Let this is SCR1, SCR1 and it carries I1 current. Okay, let this is I, total current is I. Then remaining n minus 1 SCR belongs to another category. Remaining n minus 1 SCRs are belongs to another category. Means all these n minus 1 SCRs blocks the same voltage. This is, instead of I taken this ns minus 1 SCRs. Let number of series connected SCRs. Ns minus 1 SCRs are belongs to another category. Like that I am assuming. Then let remaining ns minus 1 SCRs are carrying the same current. This is I2. Assuming that blocking the same voltage. Okay. Then this is also I. This is also I. Okay. This current is also I. This is also I current. Okay. Let, because SCR1 blocks one voltage, let assume that this SCR is carrying a minimum leakage current, IB minimum leakage current. And this SCR is carrying the maximum leakage current, IB max. The point to remember, the SCR which carrying the minimum leakage current that blocks maximum voltage. Let this is VBMX, maximum blocking voltage. Then remaining ns minus 1 SCR, this also carrying same leakage current and this also carrying, assume that same leakage current, IBMX. If any SCR carrying the maximum leakage current, then it blocks the voltage of VBMN, minimum blocking voltage. This is VBMX is maximum blocking voltage, VBMN is minimum blocking voltage. Then this total circuit is nothing but a static equalizing circuit. This resistance is called static equalizing resistance. Now I want to design what is the value of R by using this circuit. See, for generalized formula I want to derive, that's why I am assuming like this. One SCR belongs to one category, remaining n minus 1 SCRs are belongs to another category. In the sense, one SCR blocks the maximum voltage, remaining ns minus 1 SCR blocks the minimum voltage. Now if you want to equalize this into this, what is the approximate value of R we can connect? Understood? Now first I want to represent all the terms here. Tell me, what is R here? Static equalizing resistance. Static equalizing resistance. R is a static equalizing resistance. Okay. What is NS here? Number of series connected SCRs. Number of series connected SCRs. Number of series connected SCRs. Okay. Tell me, what is IBMX? Maximum leakage current. Maximum leakage current. IBMX is a maximum leakage current. Maximum leakage current. Next, what is IBMN? Minimum leakage current. Minimum leakage current. Minimum leakage current. IBMN is minimum leakage current. Yes, IBMN is a minimum leakage current. Then in terms S, what is VBMX? Maximum blocking voltage. Maximum blocking voltage. Maximum blocking voltage. That point to remember, the SCR which having all these SCRs are under forward blocking mode. That's why I am telling that this SCR is carrying the leakage current. This SCR is also carrying leakage current. This SCR is also carrying leakage current. But the SCR which carries the minimum leakage current, that blocks more voltage. That you know. If any SCR carrying the minimum leakage current means that SCR blocks the high voltage. Simple observation. Go for switch concept. For example, this SCR. Let us assume that SCR is under forward blocking mode. J1 is closed. J3 is closed. J2 is open. Minimum leakage. Minimum leakage current. Minimum leakage current means more number of charge carriers or less number of charge carriers. Less number of charge carriers at J2 junction. If the charge carriers are less, width of J2 high or less? Less. It blocks high, width of the J2. If the charge carriers are less, width of the J2 high. Once the width of the J2 is high, it blocks high voltage or less voltage? High voltage. For example, this SCR is having the maximum leakage current. If that SCR is having the maximum leakage current, more number of charge carriers at J2. Once there is a more number of charge carriers at J2, what is the width of the J2? Less. Once the width of the J2 is less, it blocks high voltage or less voltage? Less voltage. That's the reason I am telling here. SCR with minimum leakage current blocks the high voltage. SCR with maximum leakage current blocks the less voltage. There is a VBMX is a maximum blocking voltage. VBMN is a minimum blocking voltage. Minimum blocking voltage. Minimum blocking voltage. Okay, minimum blocking voltage. The another observation you concentrate here. Let no doubt at all, under forward blocking mode, it cannot carry the current. But I am assuming that one current I. This is a string current. But in the final expression, we don't get this I. But I am taking this rated current only. But we know that you have the doubt, sir. Under forward blocking mode, it cannot carry any current. But you are taking that I. This I is a string current. But in the final equation, it consists only leakage current. We don't have any rated currents. But here, let at this point, this is point A. Let this is a point A. This is point A and this is point B. At point A, I am applying KCL. At point A. What is the KCL? Tell me. At point A. What is the entering current? I equal to. What is the leaving current? I1 plus this current is IBMN. At point B, I am applying KCL. At point B, apply KCL. This is point B. This is point B. Apply KCL means what is entering current? Always string current remains constant. Series connection. Here also which current? I. Entering current is I. What is the leaving currents? I2 plus IB mx. These equations you remember, this we can use in the derivation. This point A and this point B, I am applying the KCL. This string current remains same. This I, that you can take. This also I. String current is remains same. Okay. Now, what is the design? How to calculate this R value? Tell me. What is Vs here? Vs is total string voltage. This term also you note down. Vs is total string voltage. String voltage. Vs is a total string voltage. Tell. From this, I am deriving this one. What is the value of R we can connect? Tell. What is the total string voltage Vs equal to? Voltage across 1 SCR plus voltage across Ns minus 1 SCRs. Voltage across 1 SCR is how much? I1 into R is equal to VBMX. That is I1 into R plus voltage across Ns minus 1 SCRs. What is the voltage across Ns minus 1 SCR? Each SCR blocking I2 into R, I2 into R, I2 into R. That is equal to VBMN. But I want total voltage. Then how you can write? Ns minus 1 into each SCR blocks the voltage of I2 into R. Clear? Then can write like this. Then Vs equal to I1 into R plus Ns minus 1 into from this one. What is I2 you write from this one? Tell me. You can write I2 equal to I minus IB maxima. This I am substituting. I2 equal to I minus IB maxima. That I am writing. I minus IB max into R. This I am writing from. Let this is equation 1. This is equation 2. This I am written from equation 2. From equation 2 I written this one. This I2 equal to I minus IB max. Okay. Then what is I equal to I1 plus IB minima? This I substitute like this. Vs equal to I1 into R plus Ns minus 1 into what is I you can write I1 plus IB minima. I1 plus IB minima minus IB maxima into R. Okay. This I written from which one? From equation 1 I written. From equation 1 I written this one. Then we can simplify this. Then total string voltage Vs equal to I1 into R plus Ns minus 1 into this I written like this. I1 plus take minus is common here. Sorry, take minus is common. Then IB mx minus IB mn. This is into R. This minus I taken the common. Then IB mx minus IB minima into R. This I will take this IB mx minus IB minima. Minima minus maxima. This is delta IB take. Change in current. Then what is the total string voltage? The total string voltage equal to I1 into R plus Ns minus 1 into. Then that is I1 minus delta IB into R. This maxima current minus minima current that I taken as a delta IB. Okay. Then you write like this. Vs equal to I1 into R plus that I am multiplying. Ns minus 1 into I1 into R minus Ns minus 1 into delta IB into R. I am multiplying this one. Ns minus 1 into I1 into R minus Ns minus 1 into delta IB into R. Okay. Then once again you simplify that to get one standard formula. I am doing like this. to calculate static equalizing resistance. I'm doing this calculation. Now from this you tell me, what the total string voltage? Total string voltage equal to, shall I write like this? I1 into R plus NS into I1 into R. What is NS here? Number of series connected SCRs. Minus I1 into R minus NS minus 1 into delta IB into R. Okay. Then this I1 into R cancel. Then what the total string voltage? The total string voltage equal to NS into. What is I1 into R, you tell me? I1 into R means voltage across SCR1 na. This is taken as VBMX na. That is single SCR, voltage across single SCR. NS into VBMX. VBMX is the voltage across single SCR. Voltage across single SCR. NS into VBMX minus NS minus 1 into delta IB into R. Now from this, you write like this, NS minus 1 into delta IB into R equal to, delta IB into R equal to, this you bring this side, then NS into VBMX minus VS. Then from this, what is R equal to? NS into VBMX minus VS by NS minus 1 into delta IB. This is the value of static equalizing resistance you connect in order to equalize the which characteristics? Static VI characteristics. This value of NS we can connect for approximate equalization of static VI characteristics. That is for equalization of which one? Voltage distribution in series connection. This is the resistance we can connect. Yes, no doubt. Yes. Yes. Okay. Clear? Yes. This is the static equalizing resistance for approximate equalization of voltage distribution across each SCR. This is the static equalizing resistance. How much static equalizing resistance you can connect? Static equalizing resistance, where delta IB equal to maximum leakage current or blocking current minus minimum leakage current or blocking current. This leakage current or blocking current. IB maximum minus IB minimum. Where VS is the string voltage, NS is series connected SCR. This all this terminology we can use. This much of resistance we can connect across each SCR for approximate equalization of which characteristics? Static VI characteristics. If you connect this resistance, then the voltage distribution becomes nearly equal. Then we can improve the string efficiency. This is the problem and this is the remedy. What is the problem? The problem in the series connection is, even though SCRs with the same rating and same specification, are connected in series, practically they don't block the same voltage because of unequal voltage distribution. Why they don't block the same voltage, you tell me? Because of unequal static VI characteristics. Because of unequal static VI characteristics, there exists unequal voltage distribution. Because of unequal voltage distribution, the problem is string efficiency is reducing. Now, remedy is you want to improve the string efficiency. In order to improve the string efficiency, what do you want to do? You want to equalize the voltage distribution. Indirectly, in order to equalize the voltage distribution, it is required to equalize the leakage resistance. If you want to equalize the leakage resistances, one method is across each SCR, different values of resistors are connected. But practically, it is a complex process. For approximate equalization, one value of resistance is designed, one equal value of resistance is designed. That resistance is connected across each SCR. Then that resistance is called static equalizing resistance. And this total circuit is called, which circuit? Static equalizing circuit. This total circuit is called static equalizing circuit. This total circuit is called static equalizing circuit. Then what is the value of that resistance is that R equal to Ns into VBMX minus 1, Ns into VBMX minus Vs by Ns minus 1 into delta IB. This much of resistance we can calculate. This very important formula, direct formula also important to solve the problems. You remember this formula as just like V by I formula. This voltage, this I, V by I formula we can remember. Clear? Based on which assumption I derived this one? I am assuming that one SCR belongs to one category, remaining Ns minus 1 SCRs belongs to another category. Now to equalize these two, how much resistance we can connect? With that assumption, I am deriving this formula. This is one problem and this is the remedy. Then not only unequal voltage distribution due to unequal static VI characteristics, there is unequal voltage distribution due to unequal dynamic characteristics also. During the operation of SCR means there exists a dynamic characteristics. Dynamic characteristics in the sense turn on characteristics and turn off characteristics. Even though SCRs with the same rating and same specification, practically they don't have same dynamic characteristics. Because of unequal dynamic characteristics, there exists unequal voltage distribution. Due to unequal voltage distribution, the string efficiency will be reduced. Then I will discuss this concept based on case 2. I will take that in case 2, there is unequal voltage distribution due to unequal dynamic characteristics. Then that is the cause. Then what is the remedy for that problem? That I want to discuss. Understood? Cause remedy that I discussed now. Similarly, there is unequal voltage distribution due to unequal dynamic characteristics. What is that problem? That I will discuss in case 2. Okay, that I will continue in the next session. Okay, this is one concept. In case 2 also, what is the problem? What is the remedy? With that, series connection will be completed. Okay, the problem and remedy that I will do, series connection will be completed. Later on, we'll see in detail about what exactly parallel connection. In detail about parallel connection. In parallel connection also same. What is the problem? What is the remedy? Clear? Understand? Concentrate.